Hi, in this video we begin to study the notion of parametrization of curves. Once we have entered the world of curves, it's important to know that there are many tools to study them. From a mathematical point of view, there are tools, among others, coming from differential calculus, using parametrizations, or algebraic tools, taking advantage of the properties of polynomials, or numerics, with which you can do good approximation of curves. In this course we are going to use, mainly, the tools from differential calculus and parametrizations. But what is a parametrization of a curve? Let's do an example. We begin with a curve on the plane, as the one you have on the screen. Actually, this curve represents the rail line between Madrid and Barcelona. If you are traveling from Madrid to Barcelona, there is some information which is very important. For example, departure time, say at noon from Madrid, and arrival time, say 2:45 to Barcelona. Perhaps you also want to know when you stop at the city of Zaragoza, or even when you cross the city of Guadalajara or Lérida. The ideal situation would be to know, for every value of the time t between departure and arrival, the exact position of the train. That's not so difficult today with a GPS device. With that example in mind, we can begin to give the notion of plane parametrized curve. For that, you need an interval of the real line. In our example, that was the time interval of our trip, but in general, it is any interval, even unbounded, or eventually the full real line. The variable of that interval is usually denoted by t as time, but you can use any other letter. Then, a parametrized curve is a relation between the values of the variable t and the points of the plane. That is, you assign to every value t a point of the plane, and taking into account that points of the plane have two coordinates, then you assign to every value t of the interval two numbers. Formally speaking, this is a definition of a function or a map from the interval I to the plane. And with this definition, we can give some additional notation. For example, the image of the initial point of the interval, if it exists, is called the initial or starting point of the curve. The image of the last point of the interval, if it exists, is the final point of the curve. And finally, the image of the interval is called the trace of the curve. It's important to note the difference between a parametrized curve and the trace of a curve. If one has a parametrized curve, that is a function from an interval to the plane, then the image of the interval is the trace. But if one has a trace, one doesn't recover the curve. In our example, if one has the rail line from Madrid to Barcelona, one doesn't know, for example, departure or arrival time. Space curves are defined in the same way. There are functions from an interval to the space. That is, you assign to every value t of the interval a point with three coordinates. And again, a parametrized curve and the trace are not the same. The trace contains less information than the parametrized curve. We finish this video with an example of a space curve. It is a helix. It's a very famous curve that will appear throughout the course. This is a composition of two different curves. In the first two coordinates, we have a plane curve describing a circle, whereas the third component describes the height of the helix. As we said before, the composition of both produces the helix.